Hello, data science students. I hope you're all doing well, staying happy, healthy, and safe. Today, we're going to be talking about linear regression. As many of you know, especially those who've had my classes before, I sometimes like to, as they say, wax a bit poetic, and I love a good quote. So this is something really, really interesting by Sir Benjamin Brodie in 1859, president of the Royal Society. The apex of its day of the scientific, literate, and elite. Anyway, so physical science, more than anything else besides, helps to teach us the actual value and right use of imagination. Properly controlled by experience and reflection, imagination becomes the noblest attribute of man, the source of poetic genius, the instrument of discovery in science. And this is incredibly true. This is incredibly true in terms of data analysis. So we have this innate ability to recognize patterns, and looking at data and envisioning the things that could potentially be explaining it is important to understanding, or at least figuring out, what's happening inside of your data and the reasons why it may be happening. For instance, we can look at things like this. Footsteps in the sand. Not so much the poem about people walking next to each other and someone carrying someone else. This is more literal. This is beautiful, and the reason it's beautiful is this is data. Data in one of its most pure forms. We have footsteps placed here by what appears to be a human and what appears to be a dog. Probably, since they're walking in parallel paths, probably some dude out walking his dog on the beach. Now, the cool thing is that, as we've talked about before, data is always an echo of something else. You're never actually measuring the thing you think you're measuring. It's always an echo of an echo of an echo. Data is an indirect representation of the thing you're trying to study. And this is an indirect representation of a person and their dog walking on the beach. A literal physical echo in the sand, ephemeral, temporary. It'll be washed away. But what we can see when we look at this is we can see many things. We can imagine a person walking along the beach. We can imagine their dog. But we can also imagine the direction that they were going, the path that they were taking. Each one of these footsteps is a step in time, representing physically where that person and where that dog was as they were walking down the beach. Since people and dogs tend to walk in a forward direction, we can say, okay, this happened in the past, this happened a little bit more recently, this happened more recently, all the way on up until wherever their path terminates, that being the most recent location we have for them. And we can use our imagination and see the situation that might have resulted in these patterns. But we can do this on even larger scales. Like, for instance, over here in this image of snow, we've got a minimum of 4 sets of footsteps, probably 5, and maybe even some tire tracks. Now, this is noisy. There's a whole bunch of little specks out there. A lot of them look the same, but this is sort of almost like a physical scatter plot, where instead of using little diamonds and dots and squares to represent different sets of data, they're literal footsteps. And you and I, we can look at this and we can immediately see certain patterns. We can immediately see that, well, this bird walked this way, the person with probably some sort of flat-soled boot walked this way, someone with maybe a dress shoe with a heel walked this way. We can get this information just by looking at it. Now, one of the disadvantages of computers is that they often lack imagination, and we have to find ways to approximate the things that people would do looking at this. Like immediately, you and I can look at this and we can see all of these different paths. And we can get different kinds of data from different kinds of images like this. For instance, let's look at this next one here. This is a picture I took many years ago. And it's 3 photos, I think, taken over about a 20-minute span, superimposed on each other, of the night sky. And you can see each of these little dots seem to be moving along a certain course across the sky. And you and I, we can look at this, and we can come up with a path for each one of these dots. Each one of these dots ends up having a direction, And what we see is that they're actually arcing. What we captured here was the rotation of the Earth in a series of photographs looking up at the night sky. And if you know how long it was between the first and last photograph, and you know the field of view of the camera and how long each of these little arcs are, you can calculate the rotational speed of the Earth. Not surprisingly, it's 360 degrees divided by 24 hours. But still, that data is encoded in this very, very simple image, something that's larger than we can actually typically see and slower than we can usually perceive. We can look at and collect out of this small set of discrete points that we can then turn into lines and arcs and gather more information from. We also see things like this in other information. For instance, this is a satellite image of Tuscaloosa, Alabama from many years ago when a tornado came through. It was devastating. I was actually in Mississippi, but at the time, but was very close to where this storm system started. So I vividly remember this event. And what we can see is a path of damage. Now, this is somewhat broken, it's somewhat discontinuous, but we can still look at this and you and I can see, here's where this storm went through this area. So we can look at this and get this information out of it. So this ability to recognize patterns in data in our surroundings is something that people are very, very good at. But often we want computers to be able to do this too. And we have to rely on our statistical methods to do this. And this is actually really important. In science, one of the things we want to do is we want to model how things behave. For instance, this is some data from a user study that we did several years ago now, where we're looking at how well people can detect changes in forward speed. So like if you're moving through the virtual world, what kind of change needs to be elicited before you can detect that a change has happened. And having these individual dots, this is neat, and it tells us something about, well, how people judge speeds at this point or at this point or at this point. But we want to be able to describe how people perceive something or behave for a whole range of situations, not just a small set that we've sampled. And this is where modeling things based off of single points of data come into play. For instance, we want to do this. We want to define a model that says, okay, no matter what value falls in between these dots, we can predict roughly how a human would behave, or how whatever it is we're measuring would behave at any continuous point along this range. And this is called regression. Sometimes you've probably also heard this referred to more frequently as finding best fit lines. This is probably one of the first visual statistics that you were taught in elementary school. I actually remember in, I think it was 4th grade, our science teacher, Miss Holofield, coming in and talking to us and showing us a scatter plot on the board. I think it had something to do with frogs. I can't remember. But I remember this vividly, that she's like, does the class know what a best fit line is? A best fit line is a line that runs through all, oops, I grabbed the screen. Sorry about that. There we go. The best fit line is a line that you can draw through the middle of all of these points so that it shows the direction in the center where the lines, where the points are going. And this was probably one of your first introductions to best fit lines and regression as well. It's sort of like an analog computation, taking a scatter plot and then getting a ruler out and drawing a line through the middle of those dots. Now, earlier in the class, we talked about modeling data with plots, and there's different ways of doing this. And specifically, our models typically come in varying degrees. So for instance, if we were going to try to model this data here, this is what we call our 0-degree model. And we've got our formula up there at the top. So you can see a 0-degree model is just your y value equals some constant. In this case, just a line that we've picked going through the middle of our data set. And if we keep increasing the degree of our model, oh, wrong direction, sorry. So we increase our degree to a 1. We have our y value equals some constant plus some constant multiplied by the value along your x-axis. This gives you a line, a straight line. And as we keep bumping up the degree, we get curvier and curvier lines. Now, linear regression is a specific kind of linear modeling, where we try to represent the pattern in our data using a linear equation. So how do you mathematically specify a line? Well, the most common formula you're probably familiar with is the slope-intercept. Good old y equals mx plus b. Now, not everybody probably remembers what all these values stand for, and that's okay. That's why we have textbooks and we can look things up. So, in this equation, y is the position along the y-axis of our graph, and m is our slope. So that's the change vertically and horizontally across our line. And b is our y-intercept, the point at which on the y-axis our line crosses where x is equal to 0. So these are all things you're probably very familiar with. Now, the neat thing is if you look back at our examples of different degrees of models, this looks very, very similar to our 1-degree polynomial model, y equals a plus b times x. Now remember, variables are just labels. Variables are just labels we use to represent some abstract value. And they can be named anything. So, we could easily say, well, in this case, on our slope-intercept, our b, we could just call that a if we wanted. We could call our m our slope b if we wanted. And then we have something that looks incredibly similar to, we have something that looks incredibly similar to our polynomial model. As a matter of fact, exactly the same. So our 1-degree polynomial model is itself a slope-intercept equation for a line. And we're going to stop this lecture right here and break this up into 2 parts. This is our intro, and we're going to go into actually calculating your linear regressions from a set of data in part 2 of this video. Okay, folks, we're going to cut it right there, and I hope you're all doing well, staying happy, healthy, and safe, and washing those hands and social distancing. If you have any questions, please shoot me an email. I look forward to hearing from you. Also, I've sent out several emails about this. I'm holding virtual office hours on Skype. Please come. I want to see you guys. I want to talk to you. If you have questions, I want to answer them. Just go to my website. It's linked on Blackboard. I've sent out a couple emails with it. Click on my Skype office hours button and enter your email address on the website. When you enter your email address and click the submit button, you'll be brought to a Skype conversation where you and I can talk about class or advising or whatever you need. Okay, folks, with that said, I'm going to wrap this up, and if you have any questions, just let me know, and I will see you in cyberspace.